Welcome to the memo discussion for Geography Paper 1, final paper for November 2024. Right, we are going to quickly discuss through the paper and figure out the possible responses that are relevant to the given set of questions. Like as usual, just a reminder of the setup of our papers. The paper is always structured in two sections. Question number 1, which is climate and weather, out of 60 marks. And question number 2, which is geomorphology, which consists of also 60 marks. And the last section will be the section on geographical skills and techniques, which is map work. So basically, that is how the paper is basically structured according to that setup of the paper. And as usual, you're supposed to answer all the questions in the paper. Right. So besides, before we explain some other concepts which are not very relevant to our discussion, let's go straight to our paper and figure out how we're supposed to give relevant responses to those given set of questions. Right. We're going to start with question number 1, question number 1.1. Refer to sketches A and B below. Various options are provided as possible answers to the following questions based on the influence of anticyclones in South Africa. Right. So I will briefly discuss on the anticyclones so that when we are answering the questions, we would have given you the relevant content that will assist you in answering those questions. Right. I will start by figuring out the anticyclonic conditions. Right. The question is talking about anticyclonic conditions. Basically, when you talk of anticyclones, I think everyone has got an idea of what an anticyclone is. When we're talking of anticyclones, we're talking about high pressure cells. An high pressure cell is typically an anticyclone. So whenever we're talking of anticyclones, the question here is based on anticyclones, which means we are referring to the high pressure cells. Right, if we check our sketch here, we have a typical high pressure cell. This is a sketch which shows the western part of the Southern African subcontinent and the eastern part on this side. We are saying our east is there and our west is there. And this is the interior of Southern Africa. Right. If this is the situation and we have a high pressure cell here over the interior, obviously this is our Kalahari high pressure cell, which dominates over the interior of Southern Africa. And on the west, we know to the west we have the Atlantic Ocean. So this typical anticyclone is the South Atlantic high pressure. And again, on the extreme eastern side here, we know on the east we have the Indian Ocean. And the typical anticyclone that we have is the South Indian high pressure cell. And we are also seeing that besides having these three common anticyclones that affect the weather of Southern Africa, we also have this typical cell that we find here. This is a coastal low. It's a typical low pressure cell that exists along the coast. So I'll try to explain how these pressure cells influence the weather system in just a brief discussion so that we are able to relate the content to the asked questions. Right. When you are reading and interpreting synoptic weather maps and you find a map whereby this high pressure cell is dominating over the interior here, it should give you an understanding that this is typical of winter conditions. When we have strong descending air over the interior, is the one that causes the dominance of the Kalahari high pressure cell over the interior. And how does it change? When it's summer, because of intense heating over the interior, the sun is directly overhead and the Earth's surface is intensively heated by the insolation. We tend to find that the high pressure cell is vertically displaced. The Kalahari high pressure cell is elevated into the atmosphere, what we call vertical displacement. So it's like it gets stronger as it is pushed towards the ground. But when it gets hot, because the ground now is very warm, and it's even rather very hot because of intense heating, the Kalahari high pressure cell exists in the upper atmosphere. It's no longer on the ground. It's vertically displaced because of the changes in seasons. So in winter, it will be close to the ground surface. That is where you see it being pronounced on the interior of Southern Africa. But in summer, it changes to an L over the interior here, which we call the thermal law. The thermal law is typically a low pressure cell that is caused by intense heating over the interior during the summer season. Right, and these ones also, how do they relate to the weather systems of the Southern African subcontinent? These ones, they have what we call a latitudinal shift. Latitudinal, which means they move latitudinally. We know the latitude values. Our latitude values starting from the equator at 0 until we get to 90 degrees at the north and the south pole. So these ones, they also move latitudinally. And what determines their latitudinal movement is the shift of the ITCZ, the intertropical convergence zone. As the intertropical convergence zone shifts, these cells, they are also affected, which will imply that if it is winter, remember our equator, let's assume our equator is somewhere there where there's 0 degrees line of latitude. If it's winter in the southern hemisphere, it means our ITCZ is somewhere along the Tropic of Cancer in the northern hemisphere. The sun is overhead somewhere here at around 23.5 degrees to the north. These cells, because the intense heating has gone further north, they will also tend to move further to the north. And they will be so close to land, like how we are seeing them here. They are very close to land. This is typical of winter conditions. And how do they move again when it's now summer? When it's now summer, we are saying our ITCZ is somewhere in crossing over Limpopo there, around the Capricorn region at 23.5 degrees to the south. It will also mean that intense heating is now on the southern hemisphere. And these cells, they also tend to shift further to the south, like what you are seeing here. They are now far away from land. If you check the distance here of the South Indian, it was close here to land, but here it's a little bit far away from land, which will show that it's typical of summer conditions. And also the South Atlantic, if you check, there's now a distance from it to the interior here. And if you check also the interior, there's no more high pressure cell over the interior, but now it's a low pressure cell, which we termed then thermal law. So basically, that is a brief discussion on the understanding of those two sketches as illustrated there. Right. So what is most important is for us to go to the questions and be able to figure out the possible responses in as fast as is possible so that we get to understand and justify why we are saying a particular answer is the most appropriate answer to a given question. Right. We want to move on and look at the first question, which is question number 1.11 on the first question based on those anticyclones. Right, let's come to our question and see what the question requires us to figure out. Sketch A shows typical dash conditions. We've talked about that. Sketch A, if we can check our sketch A, is a sketch which is showing a high pressure cell over the interior, a low pressure cell on the coast, which is a coastal low. And also we have, and also before I forget, the coastal low, you must also know its characteristic. It's a typical low pressure cell that exists along the coast, which moves from the western coast going to the eastern coast and dissipates around Mozambique there. That is the movement of the coastal low pressure cell. Right, they move from west going to the east along the coast. Right, so if you are going to, for the first question, we are saying the sketch A typical, which are typical conditions there. On A, there is high pressure over the interior. The subtropical anticyclones are very close to land. So which gives us C as the correct response for that one. Then we move on to the next question. The low pressure system in sketch B forms due to dash over the land. The low pressure in B here, low pressure over the interior in B, I think I have highlighted that earlier on, is caused by intense heating. When there is intense heating during summer, that low pressure cell develops, which we call the thermal law. Right, we move on to the next question. Dash is the concept used to describe the elongation of the isobars associated with the South Atlantic anticyclone in sketch B. Right, if you check a sketch B, how are we relating to the elongation? Right, what we call an elongation, if you check the distance from the center of our high pressure cell to the outer lying isobar here on this direction, to the western direction. If you check here, the distance is relatively smaller, which means there's steeper gradient here. But if you check going to this direction here, the same isobar is very far away from the center of the high pressure cell. This is what we refer to as the elongation of this high pressure cell here. So if it's an elongation, the isobars are further spaced away from each other from the center of the high pressure cell. That is typical of what we call ridging. Is the concept of ridging, which makes C the correct response. If it was a low pressure cell and there's an elongation, that would have been a trough. So you must always know the difference there. When it's a high pressure cell, it's a ridge. And when you have a low pressure cell and there's an elongation, maybe the isobars are going like that. They are going like that away from the center is here, but the isobars are elongating in that direction. They are further spaced away from each other, and there is a low pressure cell here. This will be a trough. But in this instance, we are having a ridge because it's a high pressure cell giving us a ridge. So basically, that's the difference between those two concepts of a ridge and the concept of a trough. Right, we'll move on to the next question. The question says, the anticyclones in sketch A and B change their position seasonally because of the, I think we've mentioned that earlier on again. The correct response is the shifting of the ITCZ. We've talked about that in the short discussion. Right, let's move on to the next question. Right, number 115, it's talking about the South Indian anticyclone. South Indian anticyclone in sketch B is likely to feed more moisture over the east coast in comparison with sketch A because it, right, if you look at how the South Indian high pressure is located in sketch A and in sketch B, there's a difference there in terms of the location of the South Indian. Right, if you check in sketch A here, the South Indian is just close to land here. It's just very near to the interior. But if you check in sketch B, it's further away from the interior. So we are saying in sketch B, the South Indian is able to feed in more moisture on the eastern coast as compared to how it feeds when it's on that position as in sketch A. Why is it like that? So if you are to figure out here, the difference is the distance that you are seeing here. Here it's further away from the interior and here it's more closer to the interior, which will mean that it is able to pick up more moisture because of the distance in sketch B. It's going to pick up more moisture because it's feeding in air from a longer distance. The longer the distance, the more the moisture the air is going to pick as it is being fed into the interior. But here, if it's closer, it means chances of the air picking more moisture are limited because it's traveling over a shorter distance for it to get to the interior. So if we are checking our responses, you will find that the correct response for that question is the correct response there is B, has a larger fetch or distance. It has a larger fetch. It is able to fetch more moisture because of the distance in B. But in A, it has a smaller fetch. Right, we go to the next question. The low pressure system in sketch A will move in a dash direction. Low pressure system in sketch A will move. The low pressure, we said it's a coastal low, and we have talked about the coastal low. We don't need to waste time. We said the coastal low, they do move from the west going to the east and along the coastal region. So the correct response is in an easterly direction. Easterly direction is the same as west to east. They move going towards the eastern direction. That is the movement direction of the coastal low. They start on the western coast around the Atlantic Ocean. They move along the coast and they will dissipate around Mozambique. Right, we got number 117. 117 is talking about the backwinds. The backwinds, typical South African winds, which are hot, gust, and dry winds, which form as a result of adiabatic heating of descending air from the plateau as it gets to the coastal region. Right. And also what you should note with the backwinds, I think we can just summarize the backwinds. The backwinds, they form from the interior, you know the shape of the landscape of South Africa, right? The sea is there, and this is our coast. And this is our interior. We are on a plateau here. And remember, we have an escarpment. So we are saying during winter season, that is where we experience the coastal low. It means it's a low pressure cell that is existing on the coast here. This is the boundary of the sea and land. We have a low pressure cell which is existing on the coast. And remember, during winter, we said we have strong descending air of the Kalahari high pressure cell, which will imply that if we have high pressure here and low pressure on the coast, there is pressure gradient. There is a tendency of the air flowing from high concentration going to lower concentration there. And because of the escarpment here, the distance from the coast to the plateau here is a pronounced distance. It's a longer distance of descent. That will imply the concept of adiabatic heating. The air will heat adiabatically as it descends the plateau, the escarpment, until it becomes a hot wind as it gets to the coast. That is typical of the back winds. It's just a short background so that you can understand how we are supporting a particular answer as to it being the correct response. So the backwinds are most likely to develop in sketch A because of the presence of the dash and the dash. Which two conditions there? We have talked of the Kalahari anticyclone. It's a factor which favors high pressure over the interior and creating pressure gradient. And also we have the coastal low. So our two correct responses is item number 1, which talks about the Kalahari, and item number 2, which talks about the coastal low. So these two, they are matched with item A. Item A becomes our correct response to that particular question. Right, we'll move on to the next question. The inversion layer that forms over the escarpment in sketch B will favor the formation of dash and a dash. The inversion layer that forms, I think we do not need to spend much time there. In sketch B, it's typical summer conditions. We are saying this is our interior, this is the coast, and this is our Indian Ocean, and this is the interior. The inversion layer during the summer season, because of the displacement of the Kalahari high pressure cell, the inversion layer will be above the plateau. This will be our inversion layer. And as there's an inversion layer which is above the plateau here, it means warm and moist air is now able to get through to the interior. The warm and moist air is going to form clouds over the interior here, which are going to produce a rainfall. Or we can also talk of the feeding in of warm and moist air here from this side, and also the feeding of cold and dry air from the Atlantic, South Atlantic high pressure here. If these two air masses meet, they tend to lead to the formation of the line thunderstorms, which are typical traveling disturbances that happen during summer. Line thunderstorms and the moisture front. So what typical conditions do we experience when we have the feeding in of warm and moist air from the east and the cold and dry air from the west? If they happen to meet, or if there's just feeding in of warm and moist air from the Indian Ocean, it gets to condense and it forms typical wet conditions over the interior. We are likely to experience rainfall and most likely to experience hail. So the correct response there is item 2 and item number 4, which comes at option item number 2 and item number 4, which comes as a response number C. Right. So basically that was the first section. We go on to the second section. Right. What we need to note there, we just have to discuss briefly on the content relating to the question and maybe just summarizing so that we give a justification as to why we are saying that's the best possible answer to that particular question. Right, match the descriptions below with the sketches A and B. Write only A or B next to the question numbers. Right, what happens with sketch A? Sketch A is typical, both the sketches, they are typical of valley climatic conditions. And we know that the valley climatic situation differs between the day time and the night time. So we need to figure out which one is typical day and which one is typical night, and what kind of wind do we experience and what kind of wind do we experience on the other extreme, and what are likely conditions to develop and what likely conditions to develop on the other extreme before we attempt the questions in brief quickly. Right. What happens in valleys is we are looking at typical valley conditions that are experienced in winter. And remember, in winter, we apply the concept of slope aspect because the sun is lower in the atmosphere. The sun does not go overhead in valleys to produce insolation that is going to hit the whole valley. But rather, if we are looking at a situation in the southern hemisphere, we are considering the aspect, the factor of the geographical factor of slope aspect. What is slope aspect? I think I still remember when you talk of slope aspect, the concept of slope aspect. We are looking at, when we're talking of slope aspect, we are looking at the orientation of a slope. Orientation of a slope. Where is the slope facing? We know that in the southern hemisphere, north-facing slopes are the ones that receive insolation during the winter season because the sun will be further to the north, which means we are assuming that our sun maybe is there, and this slope is in the southern hemisphere, which means southern direction is there and northern direction is there, which will mean that the sun's rays are able to hit only this part of the slope. And this side does not receive insolation because it's facing away from the sun. So basically, this becomes now a side which we call the shadow zone. And this is now the zone of incidence. Zone of incidence. Given this, it will create a situation whereby we have the development of two different pressure systems within the valley. If the valley side is heated, it is going to become warmer, which will promote the development of low pressure on the valley side. And given the valley floor, there is no insolation being received in the floor here. It will also mean that the pressure, there will be pressure gradient. The valley floor will be colder compared to the valley side. And that will imply that the air has to move from the valley floor going to the valley side because there's now pressure gradient. The insolation that has been received on the valley side has caused the development of a low pressure cell. And in the valley floor is relatively colder because there's no insolation. There is now higher pressure and the wind will tend to move in a particular direction. So what I'm explaining here is typical of what we have in sketch B. The wind is going up the slope because there is high pressure in the valley floor. There is no heating taking place here, but there is heating taking place here. It's during the day, creating a low pressure on the valley sides, meaning to say we now have an upward movement of air from the floor to the side. This is typical of day conditions. And the reversal will be true during the night conditions. This is typical of night condition. Now, during the night, the valley sides, they lose heat because of long wave or terrestrial radiation. There is excessive loss of heat from the valley sides. But in the valley floor, there's little effect here of radiation, which means now the valley floor is warmer than the valley side. Air, which is immediately above the valley side, is excessively cooled by the cold conditions which has been created by long wave radiation. And now it means the pressure system reverses. We now have a high pressure on the valley side, and we now have a lower pressure in the valley floor, prompting the air to move in that direction, which will mean that now this is a downward movement of air from the valley side to the valley floor. And this is typical of what we call the katabatic wind. And this is what we call the anabatic wind. So you don't need to confuse those two. Anabatic wind is an upslope wind, which is a typical wind that are experienced during the day. Then a katabatic is a downslope wind, which is typically experienced during the night. And what implications does it have? The katabatic, because it's a very cold wind, which is coming from a region which has been excessively cooled by the long wave radiation, it is going to create frost pockets in the valley floor. Whenever dew point temperature is below freezing point, it means the moisture is going to turn into ice and it's going to create what we call the frost pockets. And again, the warmer air which was in the valley is going to be displaced into the upper atmosphere here, but not out of the valley, creating this belt here, which we call the thermal belt. The thermal belt, why doesn't this air here escape from the valley? There is strong descending air, which is heavy because of the katabatic wind. This air is dense, it's going to displace this warmer air because it's less dense. But however, it's not going to escape the valley because of the strong descending air coming from the Kalahari high pressure cell. So when you talk of the thermal belt, you are saying this is a zone of warm air which is trapped between two cold air masses. There's cold air from above and there's cold air from below, and the warm air is trapped below, in between what we call the thermal belt. Right. So typically that is the situation with the valley climates. We are not discussing content. We must focus on answering our questions. But the background to the content is very important so that you at least understand where the responses are coming from based on geographical arguments which are tangible. Right, let's go to our answers to the questions. Right, the first question is saying, represent anabatic. We've talked about that. Anabatic is B. Anabatic is the day situation. And in upslope, which is B. Cold air forces the warm air to rise, which forms an inversion. We talked about that. It happens in A. Occurs during the day due to insolation. It is B. We've talked about that. Frost forms on the valley floor when temperature drops to below 0. We've talked about the frost pockets. They happen in situation A. So basically, those are our correct responses. We move on to the next question. Right. Our next question is based on the pollution dome. Right. I will briefly describe the pollution dome and how they differ from the day situation to the night situation. Just to give a background to the two concepts of the day situation and the night situation of a pollution dome. But what we should note before we answer those questions, do not confuse a pollution dome with an urban heat island. That is a typical confusion that most learners typically have. When you're talking of a pollution dome, do not confuse it with an urban heat island. Those are typical urban climatic conditions. They are related, but they're not the same. Pollution dome. What is a pollution dome? We are looking at the concentration of pollutants over a city. Pollutants are concentrated in a city or in an urban area. That is a pollution dome. And what is an urban heat island? The concept is based on the term heat here. Heat, we are talking of temperature. An urban heat island is an urban area that has got a higher temperature, average temperature, compared to the surrounding rural area. We are saying in the urban area, the temperatures are relatively higher. The average temperatures are higher compared to the surrounding rural area or the surrounding farmland. That is an urban heat island. So do not confuse the two. So this is typical of a pollution dome. The pollution dome, what happens is, remember during the day we have very high temperatures in the cities and in the towns because of the effect of urban heat island. The artificial surfaces that we have in the CBD and the density of the buildings, and also the absence of natural features, natural temperature regulating features like water bodies and vegetation. It contributes towards higher temperatures. And also, if you talk of emissions from vehicles and also industrial emissions, they contribute towards the absorption of heat in an urban area. So at the end, there will be higher temperature in the urban area. And what is going to happen to the pressure? The pressure in the urban area is going to be lower compared to the surrounding areas. This is the rural area and this is the rural area. In the rural area, it's relatively cooler because of the natural surfaces and because of the cooling effect of water bodies. It means that now there's a higher pressure in the rural area and the surrounding rural areas got a higher pressure, but the urban areas got a low pressure. So it means there will be now pressure gradient and the air comes from the surrounding rural area to feed into the low pressure. It converges and it rises, circulating in a clockwise direction, and the air is displaced in the upper atmosphere. So as the air moves like this, it is also going to take with it pollutants, which are released in the city here. The pollutants are going to be blown by the incoming air, which is converging and rising, and they are going to be displaced. They will be less concentrated because they are being taken into the upper atmosphere because of this vertical updraft of the converging air in the urban area. But during the night, this pressure system now does not exist. Because now during the night, there's no more insolation and there is no more activities that are contributing towards the release of more and more pollutants in the city here. And mainly because of the reversal of the pressure system, the low pressure is no longer acting. And now, which pressure now is now acting is now the Kalahari high pressure cell. The descending air is now the one which is more active. Because of the strong descending air, the level of the pollution dome now, the pollutants are now lowered because there is descending air. Sinking air is forcing the pollutants to go lower and lower to the level of the buildings. And because of the space here, the pollutants are now closely packed and are now at a lower elevation because of the strong descending air, which is forcing them further down, which will mean that the effect of pollution domes is more pronounced during the night than during the day. During the day, the pollutants are dispersed vertically into the upper atmosphere, but at night, they are concentrated because they are now being pushed down by the strong descending air from the Kalahari high pressure cell. So that is the difference between the pollution dome situation during the day and during the night. So this is typical of the day situation, and this is typical of a pollution dome at night. Right, let's go to the questions and figure out what's the best possible response to those questions. Right, represents a pollution dome at night. I think the response is there. A pollution dome at night is the one indicated on B, like what is indicated here. The night situation is the situation at sketch B. So our response for this one is B. Then pollutants are dispersed. That happens at A. We've talked about that. Denser concentration of pollutants over the urban area. It happens at B during the night. Those are the possible responses to the question. Let's move on to the next question. Right. The next question is on a cross section of a mid-latitude cyclone. Right. Mid-latitude cyclones, we do not need to waste time on them. I think you have the knowledge of mid-latitude cyclones. We cannot discuss the whole thing. Right, let's look at the questions. In which general direction do mid-latitude cyclones move? Right, do not confuse a mid-latitude cyclone with a tropical cyclone because those two are not the same. A mid-latitude cyclone, remember mid-latitude cyclones, they originate over the Atlantic Ocean and they affect the western Cape of South Africa into the interior. And tropical cyclones, they occur over the Indian Ocean. They affect the eastern part of the South African subcontinent, mainly Mozambique into Zimbabwe into South Africa, or sometimes into Malawi. So those two weather systems, they have got distinct movement directions. A tropical cyclone moves from east to west, or it moves westwards. That is a tropical, but that is not our question. Just for clarity, a tropical cyclone is from east to west or westwards. But a mid-latitude cyclone, this one in the question, is from west to east or is eastwards. That's the difference between those two. Right, so this one, general direction, you can say from, you can say eastwards, or you can say west to east. It's basically the same. That is the movement of. Give a reason for your answer. Why do they move in that direction? Right, I think you still remember from grade 10, we did the global, you did the global air circulation model. The planetary winds. We have a belt of the tropical easterlies or the trade winds. We have a belt of the westerlies and we have a belt of the polar easterlies. The winds which are responsible or which have got an influence over the movement of the mid-latitude cyclone, if you can refer back to the global air circulation, they are influenced by the westerlies. They move under the influence of the westerlies. They're influenced by westerlies. I think for those who follow my previous discussions, I did a discussion on the prelim for Gauteng paper 1, where there was a question which was asking about the winds responsible for the influence of the mid-latitude cyclone. And on the response, there was tropical easterlies and the polar easterlies. Polar easterlies was regarded as the correct response because it was a choosing question. The responses were there. But geographically, the winds which are responsible for the movement of the mid-latitude cyclone are the westerlies. Though the polar easterlies are there on the formative stage of the mid-latitude cyclone, but they do not influence their movement. So the correct response is there. They are influenced by the westerlies. They move from west to east under the influence of the westerlies. In tropical cyclones, they move from east to west under the influence of the trade winds, or which we call the tropical easterlies. Those are the driving force of tropical cyclones for them to move from east to west. They are driven by the trade winds or the tropical easterlies, and these ones, they are driven by the westerlies. Right. How does a front A gives rise to the formation of cumulonimbus clouds? Right. This question requires you to know how cumulonimbus clouds look like, and you relate them to how the front also looks like. Right, if you check here, let me just make a clear illustration so that I can explain something tangible. The cold front is like this. This is our ground, and let's say a warm front is somewhere like this. So we are saying this is the warm sector of our weather system, and this is the cold, and this is the cold sector. And this system is moving in that direction, from west going to east. This front here, it moves faster because there is colder air behind warm air. But warm air here cannot effectively push towards the cold air on the other side here. So the warm front is slower, while the cold front is very fast, which will imply that there is squashing of the space of the warm sector. The warm air will be gradually displaced from the ground because of the fast movement of the cold front towards the warm front. And that will imply that this space, if it's becoming limited, the only space that will be available for warm air to occupy will be the upper atmosphere. And how does the warm air get displaced given the gradient of the cold front and the gradient of the warm front? It means here, the warm front is, the cold front is going to displace the warm air almost vertically because it's steep in gradient here. It has a steeper gradient. So as it has a steeper gradient, while it is forcing warm air it's displacing warm air from the ground surface, the warm air is displaced almost vertically. There are vertical updrafts that are going to happen because of the gradient of the cold front. While it's here, there is gentle gradient, the warm air is going to be displaced gently into the atmosphere, which will imply that the nature of clouds that are going to form on the side of the cold front won't be the same as the clouds that are going to form on the side of the warm front because of the differences in the nature of gradient of the cold front against the warm front. Here, we are going to have condensation taking place. Let's assume this is our dew point level. The clouds will start to form from here, and the vertical updraft will continue going up and up until the moisture is finished, which means we are going to have towering clouds, clouds of large vertical extent, which are typical cumulonimbus clouds. So in your explanation, the question is saying, how does front at A give rise to the formation of cumulonimbus clouds? Explain the steepness of the cold front. The cold front has got a steep gradient. And what is the implication of the steep gradient? Warm and moist air. Warm air is forced to rise steeply. And what is going to happen with that steep rise of the warm air? Condensation occurs. And clouds of a large vertical extent develop. Which is the cumulonimbus cloud. So basically, you should explain the steepness of the cold front here, and its impact on the upliftment of the warm air. It is going to uplift the air almost vertically, and which will also imply that the clouds which are going to form are going to have a large vertical extent. We are going to have towering clouds, very tall clouds forming on that part, which is a feature of the cumulonimbus clouds. Like if you can check on the sketch there, the cloud is towering. It's a tall cloud. If you can check from your illustration there, if you check here, this typical cloud here, you can see condensation is happening starting from there, and there is vertical upliftment of air. The air is almost being lifted vertically. So it will mean that the cloud will keep on forming until the moisture is depleted in the rising air. So the cloud will also be a towering cloud. Unlike this side here of general gradient, you see the cloud is not of a vertical extent. Right. Let's go to the last question. Last question is saying, in a paragraph of approximately 8 lines, explain the strategies that can be put in place to manage the negative environmental impact of the heavy rainfall associated with mid-latitude cyclone. Right, I want you to analyze the key aspects of the question here. Do not overshadow these questions and neglect the key aspects of the question. You end up answering the question wrongly. You must address, the question is very specific, and you must also be specific in your response. Attempt what is only asked by the question. Do not attempt what is not required by the question. Answer the question. Right. So what is the question? Strategies that can be put in place to manage negative environmental impact of what? Of heavy rainfall. That is where our key aspects on the questions are. We want to come out with strategies to manage the negative environmental impact that is caused by heavy rainfall. So our focus should be on negative aspects on the environment. How heavy rainfall's impact, how heavy rainfall's negative impact on the environment can be managed. So when you are answering that question, you should find strategies which will have a positive implication on the damage that can be caused by the heavy rainfall on the environment. So we can talk of strategies like widening river channels to increase their discharge capacity. What are we doing here? If we are widening the river channel, it means we want to avoid the impact of heavy rainfall causing flooding on the adjacent environment. If the river is wider, it means it has capacity to contain more water, and it will limit the overflowing of water from the rivers into the adjacent lands or into adjacent the natural environments. And also, we can talk of planting trees. How can planting trees is of important? We want to try and reduce soil erosion. The natural environment is going to be affected negatively through soil erosion. If there's heavy rainfall, there's more surface runoff, the soil is loose and is not covered. It will mean that we have a high risk of soil erosion on the environment. So if you plant trees and vegetative cover to reduce soil erosion on the environment, or we can talk of dredging and straightening rivers. Dredging and straightening rivers to reduce flooding. Winding rivers have got more risk of flooding than straight river channels. And also we should remove material from the rivers so that the rivers flow effectively in case we have heavy rainfall, which is coming from the mid-latitude cyclone. And also we can talk of temporary measures like sandbags to prevent flooding. Or we can also talk of flood resilient infrastructure. There we can talk of building levees, the artificial levees. We know the natural levees, which is the natural embankment on the river channel. We can also do the artificial one, where we try to build our walls, the protective walls, the flood walls along the river channels to try and contain all the water within the river channel so that we avoid excess water getting to the environment or damaging the surrounding. So those are some of the strategies that we can try to put in place. Or we can also look at land use zoning or buffering. So that there's less damage. If rivers are buffered, we do land use zoning. We do not interfere with the activities of the river. It means we will manage the river and it will be able to effectively flow without harming the negative environment, causing negative implications on the environment. So basically, that is how you can attempt to answer that question, right? But the question is specific, and also remember it's a paragraph question. Paragraph question is continuous writing, and you should always remember that when you're answering, give a factor, which is an answer to the question, and you should qualify that particular factor. How does it answer the question? You give an answer, and how is the answer answering the question? How does it qualify as a correct response to the question? It means you are further shedding more light on the response. We are further qualifying the factor for it to be a relevant response. Right, so we are done with question number 1.3. Let's go to question number 1.4, which talks about tropical cyclone Filipo. Right, the question is based on a typical tropical cyclone which affected Mozambique, made the landfall of Mozambique on the 12th of March and strengthened on the coast of Southeast Africa, bringing strong winds and heavy rain to Mozambique. On March 13, tropical storm Filipo moved back over the ocean, developed into tropical cyclone at 14 March. Right, the infographic here is everything. State one condition that could have led to the development of tropical cyclone Filipo. Right, here we're looking at conditions necessary for the formation of tropical cyclones. What conditions do they need for them to form? They need warm oceans with a minimum temperature of 26.5 degrees Celsius for them to effectively form. So that is why they form over the Indian Ocean where there is warm water. And also there is need for Coriolis force. To facilitate the rotation of the system, there's need for Coriolis force. And that is why we say tropical cyclones, they don't form within the belt of 0 to 5 degrees north and south of the equator because there is limited Coriolis force in that region, is almost zero. The deflective frequency of Coriolis is almost zero. It increases as we go to the North Pole and the South Pole. So tropical cyclones cannot effectively form within 0 to 5 degrees of the equator because of the limitation of Coriolis effect. And also we can talk of the abundance of moisture over the warm ocean is also another factor favoring. And also the presence of light variable winds to facilitate the formation of the vortex. Light variable winds, they are also a required factor which will facilitate the formation of the vortex of the system. Right. So the question basically was asking for any one conditions which favors the formation or of the tropical cyclone. Give evidence from the map and table of information that tropical cyclone had strengthened from 10 to 11 March. Right, let's go to the infographic. From the 10th and 11th of March, it shows that the tropical cyclone had strengthened. Right, let's check from the map here. The 10th of March, it's here at 12 o'clock. And to the 11th of March is here until 6 o'clock, 1800 hours. So in this period here, we are saying the tropical cyclone strengthened? Give evidence from the map and the table. Evidence from the map that the tropical cyclone strengthened. What can we use there to substantiate that the tropical cyclone was strengthening? Basically, we are seeing that the tropical cyclone is moving over the warm ocean. From the 10th of March to the 11th of March, it was right through over the warm ocean, which will also mean that there will be more feeding in of moisture into the system, and there will be more release of latent heat, which will further strengthen the system. So which means from the 10th to the 11th, the system was strengthening because it was moving over the warm water body where there is no friction. Remember, it's a flat surface where there's no friction. There's nothing that is causing a drag on the weather system. It's flowing smoothly over the water body and is gaining more moisture because there's feeding in of moisture from the warm ocean, and also latent heat is being released, which will further strengthen the system. So it's clear evident that the system was moving over the warm ocean and those factors were present, meaning to say the system was supposed to strengthen during that particular period of time based on the map. And if you come to the table here, we can see that on the 10th of March, the wind was at 65 kilometers per hour. On the 11th of March at midday, it was now at 95. And by 1800 hours, the wind had further strengthened to 116 kilometers per hour. This is also evidence of strengthening of the weather system. From the 10th of March at midday until the 1800 hours of the 11th of March, the wind speed of the weather system was increasing from 63 kilometers per hour to 95 kilometers per hour to 116 kilometers per hour. It's also evidence from the table, which shows that the system was strengthening as it was moving in those particular given days. Right. Then we'll go to the next question. Give two reasons for the decrease in wind speed from 600 hours to 1800 hours on March 12th. Right, let's go to, if we check here from 6 a.m. to 6 in the afternoon, on the 12th of March, the wind speed was declining. It was 95, and then it was now 74. During the morning, it was at 95 kilometers per hour, and it further declined to 74 kilometers per hour by 1800 hours of the very same day. And let's go to our map here. If we go to our map, we find that at 6 o'clock on the 12th of March, our system was here. It was just approaching the land of Mozambique. And if we check by 1800 hours, it was now here, somewhere in the midst of Mozambique. So we want to substantiate the fact what made that system lose its strength as it was moving over the land of Mozambique, because we are tracing the path. At 6 in the morning, it was just approaching land. But at around 6 later in the evening, it was just in the midst of Mozambique, there somewhere over land. So we are looking at the conditions that caused the system to lose its strength as it was moving over the land. That is the question, to be specific. So the conditions there, we can talk of frictional drag. There was frictional drag. Frictional drag, we are saying, the system now is moving over a rough surface. It's moving over land surface. There are mountains, there are other physical features, which will cause frictional drag. The system will be dragged by frictional force as it is moving over a surface which is rough and unsmooth. Unlike when it's moving over water, it will be moving fast because the surface is smooth. So here there's no frictional drag, which is a disturbing factor. And also, we can talk of limited moisture. Remember, we've been talking of moisture being fed into the system and strengthening the system. Now there's no more moisture over land. There's limited moisture over the land, which will mean that the system cannot further strengthen or cannot further gain in strength because of the absence of moisture. And also, we can talk of less latent heat. The latent heat released during condensation is the one that fuels the system. So now because there's less moisture, it means condensation is not effectively taking place. And because of less condensation, there's less heat, which fuels the system. So basically, if you can discuss on those aspects, that will lead you to the correct response to that particular question. Remember, it's a 2x2 question. I must give two fully explained responses. Right. Then we'll also move on to question 144. On March 14, tropical cyclone Filipo reached the mature stage. Draw a labeled cross-section of a tropical cyclone Filipo in its mature stage. Marks will be awarded for the following. You have to indicate the cross-section itself. It must have a correct shape and the type of cloud that forms, and also the eye of the system and the air movement in the eye. So I'll just draw a rough cross-section. And also remember, a cross-section is not the same as an area of view. Do not confuse the two. A cross-section is a cut view of the system. The system will appear like this. Though I'm not very good in drawing, I will try to draw something that has got maybe a meaning. Though not very meaningful, but geographically right. So we are saying these are our clouds that are going to form. And maybe the other cloud at the end there. And on the other side, we also have clouds forming like that. And also clouds are forming. Right. So let me try to make it more straighter at the center here so that what I want to illustrate will come out clear. Right. So we are saying our system like this. Right. And there's a cloud like that. Right. So we are saying this is our system. The air is feeding. This is the center of the system where there's low pressure here. And the circulation of air, remember, air circulates clockwise as it gets into the low. So which means the air is feeding in like this. It's vertically uplifted. It's uplifted. That's how the air is feeding into the system through those arrows. The air is converging and the air converges and rises, creating those bands of clouds. So which means this is a cloud. And this is another band of a cloud, and another band of a cloud. This is a band of a cloud, another one, and another one here. And what kind of clouds do we have? We have the cumulonimbus clouds forming. Those are the typical clouds that we have on the weather system. Because of strong updraft, the clouds will be cumulonimbus clouds. Then what typical movement happens at the center? We have what we call the eye. This midpoint of the system, we have a towering cloud on this side and a towering cloud on this side, but there, this is what we call the eye, where there will be clear conditions. And we have sinking air at the center of the system here. So what I'm supposed to do there is to get a mark for drawing a proper cross-section, though mine is not very accurate because of what I'm using. But if you are drawing with your pencil, you must be having an accurate and clear illustration, and also indicate the nature of the cloud, the type of the clouds. You label cumulonimbus a cloud, and then you label your eye at the center of the system, and also the air movement in the eye is indicated by these two arrows with descending air. The air is descending in the center of the eye. That is basically what you should target to get for marks for that particular illustration of a cross-section. Right, to move on to the next question. Right, account for the lack of rainfall and clouds in the eye. Why are there cloudless conditions and stable conditions in the eye of the system? I think I have briefly explained what happens in the eye of the system. In the eye of the system, there is descending air. The center of the system has got descending air. And how does descending air contribute to clear clouds? When the air is descending, there is no condensation taking place, which means there will be no clouds and no rainfall forming in the midst of the system. There is descending air. That is the first reason. The air is descending, or the air is sinking in the eye of the system. Air sinks in the eye of the system, like what I indicated. Air sinks or descends. And how does that impact? No condensation takes place. When there's no condensation, it means there are no clouds. And apparently, no rainfall. The rainfall occurs on the wall of the system surrounding the eye, but right at the center of the system, it will be having clear skies and stable conditions. Right, let's move on to our last question on climate and weather. Right, our question is based on line thunderstorms over South Africa. I think we've briefly discussed about that when we were looking at the anticyclones affecting the weather of South Africa. This is what we call a traveling disturbance, typical traveling disturbance weather systems, which are typical of summer conditions. The line thunderstorms are experienced during the summer conditions. Right. According to the extract, in which season do line thunderstorms mainly occur? Even if we don't check the extract, we know that line thunderstorms are traveling disturbances that are caused in summer season. Our answer is here. It's summer. Describe the temperature and moisture content of wind A and wind B that led to the formation of the line thunderstorms. We are worried about the temperature, and can you be articulate to the question and answer the question? Right. The first thing is you need to address the temperature, and the next thing you need to address the moisture content. So, in terms of temperature, an air can be cold or warm. That is temperature. So if we check the air which is coming from A, is coming from the South Atlantic. This is the South Atlantic. I think we've talked about that. High pressure. And this is the South Indian high pressure. And their anticyclonic circulations are going to feed in air to the interior. Anticyclonic circulation from there and here. The two air masses are going to meet. And because of the differences in their properties, one is cold, one is dry, one is warm. One is cold, the other one is warm. One is dry, one is moist. One is stable, the other one is unstable. They cannot mix. So they tend to meet each other at the front here, and the moisture front develops, which is also featured with line thunderstorms. So what are we saying here? Here we found that the answer is summer. Don't need to describe the temperature, and yes, starting with A is from the South Atlantic high. It's cold, that is its temperature, and its moisture is dry. This is A. And we go to B. What about B temperature and moisture? B, the temperature is warm. It's coming from the Indian Ocean, and the moisture is moist. So that's the difference. This one is warm and moist from the Indian Ocean. This one is cold and dry from the Atlantic Ocean. Explain why the heaviest rainfall occurs closer to the moisture front, as evident in the source. Right, we can see here, this is the situation that happens at the moisture front. If the moisture front is here, it means immediately to the east of the moisture front, there's heavy rainfall. As we keep further, the rain becomes moderate and becomes light as we further move away from the moisture front. The question requires us to give a justification as to why there's heavy rainfall closer to the moisture front. Right. I'll try to explain this by means of an illustration so that maybe it becomes clear. I'll just try to use a simple illustration so that it becomes clear why there is heavy rainfall just immediately to the east of the moisture front. Right. What will happen when those two air masses meet? We are looking at a situation whereby there is a cold and dry air which is coming from the South Atlantic high. This cold and dry air, remember, is going to cause a front which is typical of a cold front, like what we have been mentioning earlier on. Like this, so it's going to be a steeper, it's going to have a steeper gradient. So it means along this front here, our moisture front, we are going to have cold air singing. This is cold air, cold and dry, coming from the Atlantic, South Atlantic high. And the warm and moist air coming from the South Indian high pressure, which is warm and moist, is going to be forced to rise. So we are seeing there's undercutting here. This A is going under and this one is going up. And what is the nature of the front is almost a steeper front, which means towering clouds are going to form here. Clouds that produce heavy rainfall are going to form immediately at the boundary here or at the front. Here, because it's further away, the condensation will take place and there's no strong upliftment of the air here. The clouds won't be tall and won't be towering. As we move away, we have clouds which are almost layered, which produce less rainfall. So it's heavy rainfall because of strong ascendance of air. The air ascends strongly or steeply, vertically, creating clouds that produce heavy rainfall. But as we move away, the upliftment becomes less stronger, creating moderate rainfall. But as we move away, again, the ascendance becomes weaker and produces light rainfall away from the front. That is basically how you can explain that implication of why we have heavy rainfall. So it's because there's strong upliftment of air. Air is strongly uplifted, creating cumulonimbus clouds close to the moisture front that produce heavy rainfall. And as we move away from the moisture front, the upliftment becomes weaker and the clouds produce less to moderate and to little rainfall as we move away from the front. Right, let's move on to the next question. The next question is talking about what? The next question is talking about, explain why, we've answered that one. Explain the negative or negative physical natural impact of line thunderstorms. Right, the question is talking about physical or natural. You should be articulate with that particular question. Explain the negative. It wants the negatives. And what kind of negatives are required? It's negative, physical, or natural impact, which means you cannot talk of impact, negative impacts, which are non-natural here. You only need to focus on natural impacts. Explain the negative, physical, natural impact of line thunderstorms. We are looking at the negative impacts on the natural environment or on the physical environment, not on the human environment or not on social life of people or not on the economy of the country. We are only worried about the physical or the natural environment. How do line thunderstorms negatively impact on the natural environment or the physical environment? So, you know, with line thunderstorms, they are associated with heavy rainfall, which can also have hail, and also they have thunderstorms with them, and also they have lightning. So if you pick on those weather elements and try to relate them to the natural environment, you will be able to answer the question. If you know the typical elements associated with line thunderstorms, then you try and relate them to how they negatively impact on the natural environment. For example, you can talk of heavy rainfall increasing the risk of flooding, which will damage the natural environment. We talk of flooding here. You explain flooding. Heavy rainfall will lead to flooding that is going to harm the environment. Or you can talk of flooding affecting the natural ecosystem. Heavy rainfall causes flooding that will affect the natural ecosystem or will cause the disturbance of habitats. It's heavy rainfall. Or you can also look at heavy rainfall causing soil erosion. Heavy rainfall can lead to high surface runoff that increase soil erosion, which leads to poor soil quality. It's on the natural environment. Soil erosion is a natural phenomenon. It's affecting soil as a natural resource. So relate the weather element to a particular aspect of the natural environment. Or if you can talk of hail, hail can damage vegetation. The natural vegetation can be damaged. Natural vegetation is damaged by hail. Or talk of wildlife, like birds. They can be killed by hail. It's a negative implication. Or talk of thunderstorms. What is the negative implication on the natural environment? Displacement of wildlife. Talk of lightning causing natural fires, which can destroy habitats, which can destroy ecosystems, which can destabilize the balance of nature. So your question should be articulate to natural environment. Do not infuse. Remember, when you're talking of natural environment, you are addressing things like biodiversity. How is the biodiversity of the area affected? Or how are the ecosystems affected? The natural vegetation, the soil, the habitats of wildlife, the balance of nature, how is it affected? So you address those aspects and look at how they are affected by those particular weather elements so that you address the requirements of the questions and not just wander around the question, not answering the question. Right. We move on to the next question. It's now a geomorphology. We just have a rundown through the geomorphology question and try to figure out how best we're supposed to respond to those questions. Right. Looking at geomorphology, you should be familiar with the concepts, but they are equally important. You get questions on the concepts. You must be able to figure out the different geomorphological concepts and relate them to the given questions. Let's go to our question. The first question 2.11. An area drained by a river and its tributaries. We do not want to waste time. That is a drainage basin. Promotes a rapid rise in the water table. Which one promotes a rapid rise? It's a gentle gradient. A gentle gradient facilitates infiltration, which will add to groundwater storage, and the water table will rise. Upper level of groundwater, that is the water table, is the upper level of the zone of saturation. The upper level of groundwater, that's the water table. Then seepage of water into the ground is also why the correct response, infiltration. Causes reduction of surface runoff. What causes the reduction of surface runoff? If we have dense vegetation, the vegetation is responsible for loosening the soil and promoting infiltration, which means when there's more infiltration, there's less surface runoff. Move on to the next question. The confluence is located at what? A confluence, you know, it's a joining point of two streams. So a confluence is at Z here. That is where the streams are joining. A high-lying area separating two tributaries in the same river system. You should be able to differentiate between a watershed, which is also a divide, from an interflow. This question is asking about an interflow. An interflow is a high-lying area separating two tributaries within the same drainage basin or two tributaries of the same river system. Then a watershed completely separates two river systems or two drainage basins. So which one is a splitting of two streams within the same is this one here. This is a watershed. It's separating this river system. It's river A on its own, river B on its own. But this is one river system with this high-lying area splitting tributary 1 from tributary 2. So it's Z as the correct response for that one. I think we've done justice from the first part. We need to move on to the next part. So you should be very familiar with your concepts and you should be able to apply them in the given context so that you don't wander around when you get these low order questions requiring you to apply the basic concepts of geomorphology. Right, we move on to the next question. Our next question, we are going to question number 2.2. Right, question number 2.2. Various options are provided. Dash is responsible for the shape of the river valley below. What kind of a shape is that one? Right, you see our stream is somewhere deep down there in that valley. The valley resembles which shape? It's a V shape. It's deep and it's relatively narrow. So what is responsible for the shape of that? The depth of the river channel, we know it's vertical erosion. And what other element there are we interested in? There's nothing else that we're interested in. because whenever there's vertical erosion, the river channel becomes narrow and becomes deep. So this is typical of the upper course of the river where we have V-shaped valleys. So this is typical of a V-shaped valley. It is caused by vertical erosion. Remember, vertical erosion is that type of erosion which is responsible for deepening the river channel. Right. Let's go to number 2.22. 2.22 says a dash forms at the base of a waterfall. At the base of a waterfall, the lower part of the waterfall, what do we have there? Obviously, we have what we call a plunge pool. I think if you still remember a waterfall, we have a resistant rock on top, then we have a softer rock at the bottom, right? And this is the typical situation of a waterfall, happens like this. So because of this, we have the river channel flowing, water flowing like that. As it gets here, the water will plunge. And as the water plunges, for it to continue, it has to circulate here. As it circulates, it ends up creating a pool here at the bottom of the waterfall. And this is what we call a plunge pool. Plunge, because it's created by the plunging effect. Water is vertically plunging from the hard and resistant rock and is hitting over the softer rocks, creating a pool at the bottom. So that is what you call a plunge pool. Right, that is the response to that particular question. We move on to the next question. Right, the next question is saying the fluvial feature depicted in the sketch below is what? Right, if you can check there, the fluvial feature is very easy to identify. We have bands of hard rocks, a band of hard rock here, another band of hard rock there, another band of hard rock there. Those bands of hard rocks, they are happening or existing along the river channel, creating this turbulent flow of the river. The river is having a turbulent flow because of the unevenness of the river bed, which is created by these bands of hard and resistant rocks. This is typical of a landform which we call a rapid. So those are rapids for that particular question. The correct response is C. A rapid, basically, we can say it's a smaller version of a waterfall. The way how waterfalls happen is equally the same way how rapids occur, but the rapids, they will just be the smaller version. The water just plunges in a smaller perspective and creates what we call that welling effect of water, creating the white waters and that form of misty condition in rivers where we have a wide band of rapids occurring in series. Right, then 224. The flat low-lying area along the river banks of a river in the lower course, we don't need to waste time. I think this is clear. This is a flood plain. The flood plain, we're looking at the flatland adjacent to a river, which is typical of the lower course of the river, where silt material and decomposed material will get deposited as the river overfloods its banks, creating rich soils for agricultural purposes on the sides of the river, which is the flood plain. Right, we try to move on to the next question. Right, we're moving on to question number 2.2.5. Right, 2.2.5, it talks about the slope at x on the inner. We got the question. Right, you see here the slope at x on the inner bank of a meander is also referred to as, I think, the two sides of a meander. We know them. The outer and the inner. The inner, that is where there is slow velocity of flow. The velocity is slow, while it's here is fast. Meaning to say, because of its fastness, there is erosion taking place. And here, because of its slowness, there's deposition taking place. So if you are to draw a cross-section from X, cutting across the river channel, across the bend here, across that bend there, if you are to draw a cross-section, it means our river channel will look like a general slope. We go into the channel and a steep slope and something like this. This is where our X is. There's deposition happening here. there is slow velocity of water, and there is fast moving water, which creates undercutting on this side. This is what we call the undercut, and this is what we call the slip off. So our response is slip off. We move on to the next question. A or N forms when a meander loop is cut off from the main stream. What forms when the meander loop is cut off from the main stream? If we have a meander and ultimately the meander has been cut off from the main stream, I think we still remember the concept of meanders. If you are having a bend along the river channel like that, we are saying this is the loop that we are talking about. And because of undercutting, this bend is going to migrate to the north, and this one is going to migrate to the south. Again, migrate to the north, and this one migrate to the south. Boom, they've managed to catch up with each other. And now the river will flow and follow a straighter course. Instead of the river following the old channel, which was winding, now the river is going straight like this. So this part here is going to be cut off. There will be deposition here, and there will be deposition there. And it will remain with its own supply of water, but no more feeding in of water from the channel. This is what we are referring to. What is the feature which is forming here? We don't need to waste time. That is an oxbow lake. So the correct response is C for that one. Right, the benefit of natural levees is dash on the floodplain. Natural levees, these are the raised embankments on the sides of the river. How do they benefit the floodplain? They reduce flooding. Right, move on to the next question. The next question is talking about deltas form. Yes, it's deltas form at the river mouth when the following conditions occur. Which conditions facilitate the formation of deltas? Remember, deltas, we are looking at that part of the river channel where it gets into its mouth. The river branches into distributaries that are going to feed into the ocean. It's no more one distinct river, but rather it's branching off because of deposition. There's extensive deposition as the river gets into the sea, such that it appears we have like one river, the sea is there, maybe the sea is starting from there. The river now starts to branch into so many distributaries feeding into the ocean or the sea. This was one river flowing from there, but now it is branching into, this is what we call a delta in this instance. So what causes the formation of deltas as the river feeds into its mouth? Right. One, it's a shallow seabed. If the seabed is shallow, it means deposited material is going to accumulate and keep on accumulating, advancing to the direction of the river flow. So a shallow bed. And what else? Strong currents, they displace. A steep seabed is out. And a strong current is also out because it is going to remove the sediments, and the river is going to attain a distinct channel. So it's small tidal range. A tidal range, you are saying if there is a tides from the river and they don't go very far, this deposited material will sustain and will keep on branching the river into distributaries. So the correct response must be having item number 1 and item number 4, which is response number D. Right. We move on to the next question. Let's analyze those two drainage patterns. The first one, I think, is clear. It means this drainage pattern is starting from a high-lying area. Maybe it's a volcanic dome, and streams are radiating from the focal point, which is high-lying. This is what we call radial drainage. And this, if you can see, the main stream is longer, but the tributaries are shorter, and the tributaries are joining at right angles. Right, this is a trellis pattern. Right, let's go to the question. Identify drainage pattern A. We've talked about that. This one is radial. And remember the opposite of radial, the centripetal, where the streams are feeding now into a basin. A low-lying area, streams are coming from the surrounding high-lying areas and feeding into a basin in the central focal point. It's the opposite of this one. Determine the stream order at X. Where is X? Our X is here. Our stream order, this is stream number 1. It's an independent stream. It doesn't have a tributary. It's number 1, and this one is number 1 again. Number 1 plus number 1, we get number 2. So the order there at pattern A is second order. The second order stream. Right, we move on to 233. Give a reason for the direction in which streams flow in a drainage pattern A. Why do streams flow in all dimensions, in all directions in that manner? Is because streams are originating from a high-lying central area, a high-lying focal point or a dome. How does that influence the streams? The streams radiate in different directions. They tend to radiate. We are saying this is the source of all these streams. Maybe it's a caldera lake on top of a volcanic mountain. That is the source of the streams. So the streams are starting on a dome area or on a high-lying area, which means they have potential to go in any direction of the dome. One can go to the northern direction, one to the eastern, to the southern, to the west, to the northeastern, in whichever direction. They radiate in any direction. They are originating from the same focal point, which is high-lying or which is a dome area, and they will have to radiate in different directions from the high-lying area. That is why we have those streams going in those different directions. Right, we go to the next question. State 2 conditions associated, how does the joining of tributaries to the main stream differ in A and B? Check here, the joining of the streams is different. If we check here, these streams, there's a confluence here, the angle, and there's a confluence here, what's the angle, and also the other confluence there. And here, the angle, that's the difference that is required there. So in A, the tributaries join at acute angles. Acute angles, which means an angle less than 90 degrees. And in B, they are joining at right angles. And the right angle, meaning to say is 90 degrees. That's the difference there. State 2 conditions are associated with the underlying rocks that contributed to the formation of trellis in pattern B. Where does trellis pattern form? Right, a trellis pattern basically form in areas of rocks of alternating resistance. Or we are saying where we have hard and softer rocks. And also, where is it likely to form? In folded areas. Folded areas which are typically exposed to tectonic upliftment. So in folded areas where we have the anticlines and the synclines, we also have trellis forming there. And also in faulted areas, we can give an example of where we have normal faults. We have a trellis forming. So trellis implies that the main stream will be stronger and longer than the tributaries. The tributaries are limited because they are originating from an area with hard and resistant rocks. If there are hard rocks here by the side of this landscape, it means the tributaries cannot erode effectively into the harder rocks, though they will become shorter. While the main stream will be flowing over softer rocks, it will become longer as it flows along softer rocks. While these ones, they will become shorter because they are starting from areas with hard and resistant rocks. And also, if it's a fold, it means if there's a fold here, there's a fold mountain, and there's another fold mountain, and there's a graben in between. It means the main river is going to flow in the valley, and the tributaries will just start from the folded ends and will end in the main river in the valley. Or if it's faulting, it means there is a host on either side, then the valleys in the middle there. Then it also implies that the low-lying area will have the major river forming and the minor, the tributaries are just being small, originating from the sides of the fault and ending into the main valley where the main stream is going to flow along and become a longer river. Right, that was the response to 136. Let's go to question number 236. Go to question number 2.4. Right, question 2.4 is based on rejuvenation. Right, the term rejuvenation, I'll give you the basics. It's the concept. You define it according to your understanding. We cannot have one common definition, but you should address the basic requirements of the concepts so that even though the definitions are different in terms of expression, but their meaning will lead us to the same concept. When I talk of rejuvenation, we are looking at a river regaining its erosive power. And what kind of erosion are we talking about here? A river regains its vertical erosive power. Meaning to say a river has attained a grade, is now balancing between deposition and erosion, but however, all of a sudden, it gets energy again to cause erosion and to erode vertically and deepen its channel. That is rejuvenation. The river is becoming younger. It has attained a grade whereby it had balanced between erosion and deposition. It was now maintaining a graded profile. But however, because of some different factors, like for example, an increase in rainfall, or factors like a drop in the sea level, or factors like a stream pirates, the river now regains its erosive power and starts to erode vertically, deepening its channel, creating those different landforms that we might talk about in the discussion as we proceed. Right, that is the concept. We move on to the next concept, identify feature A. If you check at A here, you see there's a sudden drop in gradient. Here is going down and there is going lower. So what is likely to be feature A? That is a nick point. Or be a waterfall. A nick point or a waterfall, that is typical of a feature that we find there where there's a sudden drop in gradient along the river channel. How does feature A indicate that the river rejuvenation has taken place? What is the justification that there is river rejuvenation that is taking place? Right. This is the old grade of the river. The river was flowing at this level. But now check from this point, the river is now flowing at a new level. So what suggests that the river has been rejuvenated is the new grade of the river meeting the old grade on that nick point, on that waterfall. For this river to achieve grade again, it has to erode this nick point headwardly until it reaches a smooth concave shape. So the fact that there is a nick point here, it suggests that the new grade here, the new profile that has been created here, is meeting the old profile here. So with the river having two profiles, this profile here, which has been created from the lower course going upwards, and the old profile from the middle, maybe it's a middle course going upwards, suggesting that this river is not having a grade, is rejuvenating, is eroding vertically from its mouth going upwards. Right, describe the change that the river rejuvenation has made to the landscape at B. Landscape at B, what has happened at B there? How has it impacted on the nature of the landscape at B? Right, you are seeing that a valley in valley has developed. We have a new valley within the old valley. And the channel, how is it like? The channel is deeply cut with steep sides. If you can check here, these lines, they represent that it's a steep landscape. We are now having a new valley here, which has formed in the old valley. And the new valley now is highly entrenched on its side. It's deeply cut with steeper sides. Right. Refer to the river terraces in the sketch above. How do river terraces form? A terrace, basically, we are looking at stepped arrangement. Maybe the new channel is there. Again, it's like that. These are the terraces that we are talking about. Maybe the new channel is there. How do these terraces develop? Right, basically, the process is a repetition of a series of processes. As rejuvenation happens, we are having this channel here. I'll explain using a diagram. Let's say this is our initial channel, our original channel of the river. The river is having a wide channel like this one. It's achieving a grade. There's a balance between deposition and erosion as the river is flowing on this channel. If it rejuvenates, the river is going to create a valley within the old valley because of rejuvenation, which means now the new valley is now this one, Valley B. And remember, this part has been left because it did not erode from the bank to the bank, but it created a new valley within the old valley. This part is left. And again, maybe there's another cycle of rejuvenation. The river again regains its energy. It creates another valley in that particular valley. You see, another valley has been created here. This is now valley number C. We had valley A, which was the original, into valley B, into valley C. And let's say maybe after again another cycle, the river regains its energy. It creates another valley within the old valley. Now we are seeing we have valley D. At the end, we are having a step here, which was left from the original channel. We went to channel number B. It left again a step here. We will go to channel C. It left another step there. At the end, we are in channel D currently. And on either side is the same. A step was left, and another step was left, and another step was left. At the end, the river will have stepped sides, which we call the terraces. Because of cycles of rejuvenation, the river will be developing a new valley within an old valley, leading to formation of the terraces. So basically, that's the concept. I'm trying to give you a concept, and you figure it out how you can express it. Right, and then the last question, number 2, 4, 6. Right, the question is saying, why are some river terraces not suitable for farming? Why are some river terraces not suitable for farming? Right, I'll just try to explain here. The reasons why some river terraces is because they have limited space. After rejuvenation, maybe the new channel just leaves a smaller space as a terrace, which means it's not comfortable or it's not sufficient enough to do any productive agriculture. And also difficult in accessing water. Difficult in accessing water. Because of the deep cutting of vertical erosion, you tend to find that water sometimes will be very deep into the new channel. And it will be difficult to access because the sides of the new channel will be steep. Remember, it will be entrenched. Vertical erosion will cause the channel to be very deep, and it will make it difficult to access water to supply to farming happening on the terrace. And also, the soil becomes less fertile. Why does the soil become less fertile? Because there's no more feeding in of silt. No more additional silt. The silt which used to be provided by flood water in the old channel is no more accessing the older terrace because the river now is deeper. And it all means that the soil will become less fertile because there's no more feeding in of additional nutrients as flood water cannot reach the terrace. It's now too high. The river is now flowing at some point, at some level, which is very lower. And also, we can talk of difficulty in using machinery. Because of the nature of the slope, the sides of the new valley are very steep. Maybe the terraces which are left are also too small to use machinery. Then they are not suitable for farming specifically. Right. Those are some of the responses that you can give. Right. We move on to the next question. Right. That was question number 2.4.6. We need to move on to question 2.5. Right. Question 2.5 is basically one of what I presume is the easiest sections of geomorphology. And I always advise learners to maximize marks on that particular question. The question on river catchment and management is one of the very much easiest sections that learners must capitalize and be able to score as high marks as is possible. A 15 out of 15 is basically possible to get. Right, we're not going to go through the texts. I hope we have gone through it and you've understood whatever is presented in that particular text there. You go through it or you can check. I will just refer to it when I want to pick an extraction. Maybe if there is a section where we need to extract an answer, then we'll refer back to the paragraph. Right. What is river management? This is a concept again. We cannot define a concept the same way. It's a concept. A concept, you define it the way you understand it. But you should be able to figure out a definition that addresses the basic requirements of the geographical effect. So basically here we're looking at, maybe you can look at it as measures to protect rivers or catchment areas Why should we take measures to protect our rivers and catchment areas to ensure sustainable supply of clean and safe water? That is my own expression of the definition. I would express it as a concept as measures which are taken to protect rivers or to protect catchment areas so as to ensure that we have sustainable supply of clean and safe water for whichever purpose, domestic, industrial, agricultural. We must have clean and safe water. So what should we do? We should take corrective measures to make sure that our rivers are safe. They are safe from pollution. They are safe from toxic elements. They are safe from siltation. They are safe from any harmful element that might cause or disrupt them having capacity to supply sufficient clean and safe water. Right. So it's a concept. You define it according to your own understanding. Name one human activity in the extract that has a negative impact on South Africa's catchment areas. Right, we just want to go back to the extract and see where we get our answer. Right, our answer, we get it here. Our answer, we get it where here it talks about agricultural runoff, which carry chemicals into river catchments. So our human activity here is agriculture, is the activity that is responsible for having a negative impact on catchment areas. How does the human activity negatively impact the health or quality of water of a catchment area? We are saying agriculture, how does it contribute towards the poor health of water or poor quality of water of a catchment area? Right, from agriculture, you can argue on the effect of pesticides. Pesticides that are used in agriculture, they do affect the quality of water. They pollute the water. There are chemicals that are used, that are sprayed in crops to kill some insects or to deal with some aphids or some other diseases. But those ones, they will also find their way. They will be washed into the water sources, into the catchment areas, into the rivers. They will pollute the water sources. Then the other threat from agriculture is that of fertilizers. Fertilizers that are added by farmers to the soil to enrich the nutrients. The nutrients also get washed into the water bodies, and they will also affect the health and the water quality. Like we talk of eutrophication as the major concern with fertilizers. They affect the balance of the nutrients in water and apparently damaging the water quality. Right. So basically, those are the two elements of pesticides and also the impact of fertilizers. Right. Then in a paragraph of approximately 8 lines, suggest sustainable strategies that the government can put in place to preserve their catchment areas. What can be done to preserve the catchment, preserve a river catchment areas? Maybe one of the most important is education. Education and awareness. Teaching people on how to conserve or to preserve their rivers and their catchments, and making them aware, because sometimes people do harm, environmental harm, as a result of lack of knowledge. So people need to be equipped with knowledge and the right information on how to preserve their rivers and also how not to cause harm. And also we can talk of environmental laws. Enacting the laws and enforcing them. This is two-dimensional. We put laws into play and we enforce them. Environmental laws, like for example, finding of people who are seen damaging the catchment areas, or people are seen polluting the rivers, or imposing laws or penalties. Those are environmental laws that we can put in place. Or we can also talk of buffering. Also another important element. We buffer or use land use zoning to avoid the influence of people's activities, of human activities on the catchment areas. We buffer those areas, we fence them off to avoid people accessing them so that they do not cause negative implications on the catchment areas and on the rivers. And also we can talk of giving incentives for sustainable practice. We incentivize good practice so that we set an example for others to copy and emulate and do the right thing. We can also talk of creating protected areas. Like the nature reserves, so that people do not have easy access to those areas where we have catchment areas of our major rivers. We make them protected areas, and those areas must be strictly controlled, and people should not have access to them. We can also sustainable land use practice. There are so many things that can be done. Implementing sustainable land use practices. Avoiding land use practices that harm the environment, that harm the catchment areas. Activities like stream bank cultivation, they are unsustainable. They will harm the catchment areas, they will harm the rivers. They should be avoided. Introduce sustainable land use practices. For example, we can talk of agroforestry. It's sustainable. It helps sustain our catchment areas and our rivers. Right? We cannot limit ourselves to this, because this is a 4x2, which means if you raise 4 responses which are fully explained with the effect and the qualifier, then you get your 8 marks. But however, there are so many responses that you can give. There are so many other possible answers that you can give to this particular question. Right. So that brings us to the end of our section A, which is our theory section. We now have to go to section B and look at geographical skills and techniques, which is section B, question number 3. Right. We move on to question number 3. Our map is on lead smith, which is typical of a city in the province of KwaZulu-Natal, Utukela district. I think the map information is provided there. You can also check on the map information. It will help you to maybe address some questions. You should not ignore the map information. Then let's go to our questions. Right. If we check here, we have the first question on the closest town to Ladysmith is. Right. Figuring out where to get that answer from. That answer, you get it on the topographic map. Is not provided on the map information on your question paper, but rather we're supposed to figure out from the topographic map. That is where you get the response to the closest town to Ladysmith. So if we go to our topographic map, you come here, you check. What do you check? If you want to identify a city or a town which is closest to the given area or the distance to the next town or whatever, you check the major roads which are exiting your map and the railway lines which are exiting your map. They will be having distances to the next town or city. You check the major routes, which is mainly the major roads, be it a national road or an arterial route or a main road or a railway line. They will give you an indication of of distance to the next town. So let's check this one. This one is saying Harrismith, it's 73 kilometers by road and it's 80 kilometers by railway. This is the first one that you can see here. Let me mark it. This. We have 80 kilometers to Harrismith on rail and it's 73 by road. Right. And then we come here. We have this town indicated here. It's called, unfortunately, my map, I need to enlarge it so that it becomes more visible. It's Glencoe. Glencoe is 36 kilometers. And Newcastle, Glencoe is 36 kilometers via rail line. And Newcastle is 98 kilometers on road. Then again, we come here. We check again. It's Colenso, 23 kilometers by road. I think those are the indications of distance to the nearest towns and cities according to our map here. So we are comparing 36 to 98 to 80 to 73 and to 23. So automatically the correct response is this one. So if you check on the responses, it means your right answer is Colenso, which is response number D. According to the topographic map, your answer is item number D, which is Colenso. Right, we move on to the next question. The feature located at grid reference coordinates 283132 south and 294722 east is. Right. I will briefly teach you the skill of how to get that one. Right. What you do here, let me illustrate it. Maybe it will make sense if I try to illustrate it from the map. Let me go to the map. We want the exact feature that we find at 28 degrees 31 minutes and 32 seconds to the south, that is latitude, and 29:47:22 to the east longitude. Right. What you do here, you go to your map. We want our degree value coordinates are given and our minute value are given. What you only need to find out is the second value. Our degree and minute values of latitude are given. Like if we check here, this is 28 degrees of latitude and 31. Let me briefly acknowledge the map so that it becomes visible. Right, like this. What are we saying here? We are saying this is 28 degrees latitude and 31 minutes latitude to the south along this line here, latitude. So which means the next line of latitude, which is given here, is going to be 32 minutes to the south of latitude, which comes here at the end of the block. And the next line, which comes here, is going to be 28 degrees, 33 seconds to the south. our values are increasing going to the south. Then we go to longitude. Our first line here is 29 degrees 45 minutes to the east, which means the first line is this one here. That is 29 degrees 45 minutes to the east. And the next line is this one. It means this one is now 46 minutes to the east. And the next line here, it means is 47 minutes to the east. They are increasing going to the east. So what coordinates do we want? We want 28 degrees of latitude and 31. 28 and 31 is along this line. Remember, we pick our coordinate from the northwest corner. So we want to see where it interlinks with our line of longitude, because our latitude, we have seen that 28 degrees and 31 minutes to this south is along this line, the first line of the northern edge of our map. Then we want to identify the longitude, which is 29.47. This is 29.45, 29.46, 29.47. We pick our coordinates from the northwest corner of our block, which means our coordinates are here. 29.47 of longitude is along this line. And 28.31 is along this line. So our northwest corner is here, and it means the block that we are referring to is this particular block here. That is where we want to identify the feature at that particular point. We are worried about this block. So what you need to do here, for you to identify the position where we find 32, we want to find 32 seconds to the south, that is latitude. And for longitude, we want to find 22 seconds to the east. How do we identify this? Because these ones now are not provided. The minute values are provided, but now the second values are not there. How then do we identify where they are located? We use calculation by measurement. If you want to identify 32 degrees to the south latitude, what you do here, you measure from here to here. This is your latitude. From the first latitude to the next latitude, what is the distance? From my measurement, I got a distance of 3.7 centimeters. And you also measure from here to here to get your longitude. From the first longitude to the next longitude, you try to identify the distance there. I got it as 3.2 centimeters. And you have to measure accurately. So we are saying this is 3.7 centimeters and this is 3.2 centimeters. What are you supposed to do now, given those two figures? For you to identify this 32 degrees to the south is 32 minutes to the south, rather seconds to the south, is from this line of latitude to the next line, there are 60-second lines between those. So we are saying it's 32 seconds out of 60 seconds as a fraction of the distance that we have got from the first latitude to the next latitude times 3.7 centimeters. What are you going to get there? If you say 32 over 60 times 3.7, from my calculation, I got approximately 2 centimeters. So what do you do now? You come with your ruler, you place your ruler, your zero from the first latitude along your line of latitude here, of longitude here. For you to identify the latitude position, because latitudes are from left to right, you place your ruler along this. Identify a measure of 2 centimeters from the origin here. Your zero is here on the ruler. You put your ruler with your zero there. Find a reading of 2 centimeters. My 2 centimeters came somewhere here. Out of 3.7, it was somewhere here. So you now measure again on the other side, or if you can draw a parallel line, just draw straight, cut across on the line of 2 centimeters. That is where 32 seconds to the south is for latitude. You do the same for longitude. You want to identify the position of 22 seconds to the east. Where is it? The distance is 3.2. So you simply say 22 seconds out of 60 seconds times the distance between the two, which is 22, right, centimeters. And you calculate this it will give you, if you do the calculation of 3.2, sorry, it's 22 of 3.2 here. 22 of 60 times 3.2, you get something like 1.2 centimeters approximately. So you now bring your ruler here from the first longitude to the second longitude. Along here, your zero should come here, your ruler going in this direction. Measure a distance of 1.2 from there. My measurement brought me somewhere here, and you draw a line parallel to your line of longitude. Identify a feature where those two cross each other. So, according to my measurements and my calculations, my features were intersecting at this particular point. And what is that particular point? Is a perennial water. That is the response that I got from that particular question according to my calculations and my measurement. So the correct response is perennial water, B, for number 312. Then the mean magnetic declination for the year dash was 21 degrees 03 minutes to the west. You just go to your topographic map. You know where to find the map information. You come here on the topographic map, check the map information at the bottom. Mean magnetic declination 21 degrees 03 minutes to the west of true north as of July 2001. So when was it for? It was for 2001. Right, determine the total annual change for 2024. When you want to find total change, you simply say the difference in years. What is the difference in years? We want to calculate for 2024 minus the year on the map. We are saying it was for 2001. To see how many years have passed. 2024 minus 2001, that's 24 minus 1, which is 23 years. And what is the total change now? Total change, we are saying the mean annual change times the number of years. The magnetic declination was changing by 8 minutes to the west according to the map information, times how many years? Times 23. What is it going to give you? 23 times 8 is going to give you 184 minutes to the west of true north. And 184, this is now a composite figure, which has got degrees and minutes. We have to deduce the number of degrees from there to get the degrees and the remaining minutes. If we divide this by 60, the multiple of 60 here is 180. 6 times 3, 180, and we remain with 4 from 184. So it means it's 3 degrees and 0.4 minutes to the west of true north. That is the total annual change for 2024. The angle has changed by a further 3 degrees and 4 minutes to the west from the initial angle that was there in 2001. Right. So we got the next question. Calculate the area of the demarcated feature 6 in blocks A4, A5, and block B4. Give the answer in square kilometers. Use the following formula. Length is 3.0 centimeters. Formula. Use the following information. Length is 3.0 centimeters. The formula is length times breadth. We are already given one dimension there. Let's go to the topographic map and see where the feature is and try to figure out sense from how it looks like. Right, the feature in question is this one here. The feature which is labeled 6. This is our feature. We are already given 3 centimeters is the longer one here. This is the longer side of the feature. According to my measurement, I also found 3 centimeters to be appearing on the longer side of which is the length of our feature. Right. 3 centimeters, if you measure accurately, you would get your measurement as 3 centimeters. Then according to also my calculation, my measurement, I got 2.2 centimeters on the other side. So if you want to calculate area, I'll calculate it there on the map. At 2.2, if you want to provide your answer in square kilometers, you must make sure that you convert your measurements according to the kilometer conversion. This is a topography, it's an orthophoto map drawn to the scale of 1:10,000. And for you to convert to kilometers, 1:10,000, for you to do a direct conversion, you simply have to multiply by 0.1 kilometers. Your map distance times 0.1 kilometers. your answer will be in kilometers. If it was a topographic map, you would multiply it by 0.5. So we are saying it's 3 times 0.1 kilometers as your length. We are multiplying it by 2,2 by 0,1 kilometers, like this. So what are we going to get as a result there? 0.1 times 3, we get 0.3 kilometers. We multiply it by 2.2 times 0.1, it gives us 0.22 kilometers. So we multiply the 2 to now get our answer in square kilometers. 0.3 times 0.22. That is going to give us 0.066 square kilometers as our final response. So the trick is you must measure accurately and you must convert using the correct scale of the map and do the accurate calculation. Right. Give a reason why the expansion of the demarcated feature 6, to the question is limited in a southeasterly direction. Let's go back to our map and see where our southeasterly direction is and why it is practically impossible for that feature to expand. Right. If we are on feature number 6 and we want to figure out where our southeasterly direction is, we basically give the compass directions from 6. We are saying if we are here, our north is somewhere there, our south, our, unfortunately, that is very wrong. Right. Our north, south, east, basically our south, we're looking at southwest, at southeast. Our southeast, we're looking at this part here. Why is it impossible for this to expand to the southeast of this particular side of the map? Right. The reason here why we cannot explain the activities happening here in this block, you see, we have a river here. This river is the main reason why expansion cannot be possible into the river, because you are seeing that this block is almost close to the river. The distance from this block to the river is a limited distance. Remember, the scale is 1 to 10,000 here. So it's just close to it's almost closer to the river. It cannot expand into the river. So the main reason why it's impossible there is there is a Clip River. Clip River is just there. That is the reason of Clip River. It cannot expand here because there is Clip River there. Right. We are done with the first part. Let's go to the next part, number 3.2.1. The temperature at F in the center of the town is 2 degrees Celsius higher than that at G. We are referring to the topographical map. The temperature at F is 2 degrees Celsius higher than that of G. Right, we are seeing where F is and where G is. Our F, you can see that is in the midst of the city here, and our G is in the outlying center here, which is almost at the river, at the meander of the river there. So the temperature here is said to be 2 degrees Celsius higher than here, which means the average temperature may be, if the average temperature here maybe is 30 degrees Celsius, it means here is 28 degrees Celsius. So the question is saying, name the concept that describes the difference, this difference. The difference here that this is a surrounding rural area, this is an urban area. We have earlier on talked about that. It's basically that we are repeating the same thing that we have been discussing under climate. So the concept here, we have calculated everything there. Give the concept which is being required by that particular question. The correct concept there is the urban heat island. Is urban heat island. That's the correct response. Is the urban heat island. It describes an urban area with a relatively higher average temperature compared to the surrounding rural areas. Then give one reason why the high density of buildings at F generally contributes to the higher temperatures. The buildings are highly concentrated. Why do they contribute? Why does that contribute to higher temperatures? We look at absorption by the buildings. The buildings, because they are concentrated, they absorb more heat, which will lead to an average rise in the temperatures because of the absorption of heat by the buildings. And also, we can talk of reflective surfaces. The buildings have got reflective surfaces, like glass and shine surfaces. They do reflect the heat, which will also contribute towards higher temperatures in the built-up area. Then number 322 is talking about explain how aspect of slope determined the location of Ross Park at 7 on the orthophoto map. Right, we got the orthophoto map and see area 7. He's saying area 7 here. This is where our area 7 is. How? The question is saying, explain, it's question number, it says explain how at area 7 on the orthophoto map. Right, we're looking at slope aspect, the concept of slope aspect there. The location of Ross Park at 7 on the orthophoto map. When we're looking at the concept of slope aspect, we are talking of orientation. This is a north-facing slope in the southern hemisphere. How does north-facing slope facilitate the development? How did it facilitate the development of that particular settlement? It's because the north-facing slope is warmer in the southern hemisphere and therefore facilitates development of settlements. This is a north-facing slope. It's facing to the north. And this map is a southern hemisphere map, which means this part receives insolation from the sun and is warmer than the other side, which is south-facing. So we're looking at slope aspect as the north-facing slope. Right. The demo indicates that the river is flowing in a dash direction. We are referring to the dam at H in block B1. Right, we check on the dam at H in block B1. Right, this dam here, the dam wall is here. Which direction is this river flowing? The side where we have the dam wall is where the river is flowing towards. Where is this dam wall? Is to the southwestern direction. Water is captured before the dam wall. So the water is accumulating on this direction while the wall is there, which means the river is going in that direction. It's coming from this direction and is going in that particular direction. So it means our correct response there is A, which is south westerly direction. The southwesterly direction. Right. We go on to the next question. It talks about question number 324. A weir is used to regulate or control the flow of water in a river. Explain why the construction of the weir was necessary. Right, why was the weir necessary in block A3 on the topographic map? In block A3, go and check A3. There's a weir which is here. Let me just wrap off this. Why was it necessary to control the flow of water in that particular stream at point, that particular point where there's a weir there? That's the question. Question is asking about the validity of constructing the weir there. So most probably if a weir is here, it means we are regulating the flow of water downstream here, which will also imply that the main reason there could be avoiding possibility of flooding downstream. If you can regulate the flow of water, it means we're also regulating the risk of flooding. Remember, there's a dam there. That dam, if the water is not regulated, it can have a risk of the wall being overwhelmed by the volume of water and creating a flood situation. So it's there to control or regulate the amount of water to reduce the risk of possibly flooding downstream. Then identify the fluvial landform feature. Refer to the section of Clip River on the orthophoto. We are looking at the orthophoto here. Clip River, we are looking at which section? Let me erase this information here. We are looking at the section of Clip River on the orthophoto map. It says from 8, let's check where our 8 is, right, to 10. Right, if we check here, our 8 and our 10, they are indicated here. Identify, refer the section of the Clip River from 8 in block A2 to 9, from 8 to 9 in block A5, right, from 8 to 9 there, 9 is there. We're looking at this section of the river, coming from 8, straight is going there, it comes here, it comes there, it comes there, then it goes to 9. This is the section that you are worried about. From point 8, the river is going in that direction until it gets there to 9. Right. Identify the fluvial landform or feature. Definitely, that is a meander. You don't have to argue there. The river is winding. It's taking a winding path. That is a meander. The river is meandering. Right. And give evidence why this fluvial feature in your answer to question 235 developed in this area. Why do we have a meander in this area? Let's check the contour lines. We only have one contour line here. The next contour line is somewhere where there's not even a contour line, it's a river. And it's the same contour line which is again coming back here. And the next contour line is there. So this spacing of contour lines, what does it tell us? It tells us that the area has got a gentle gradient. It is a floodplain. Remember, meanders, they form in the lower course of the river where gradient is very gentle. So this area is a gently sloping landscape, which implies that meanders are likely to form in that particular area. That is the justification. Right, refer to block C5 on the orthophoto. Why will more erosion take place at 11 than at 10? We are looking at this part here. I think, again, we've explained something in relation to that. This is a meander, and on the meander, this is the inner bend, and this is the outer bend. The question is now asking, why is there more erosion at 11 than at 10? What causes erosion here is there is high velocity of water in the channel. The river flows at a high velocity here, and there's more erosive power than at this point. Here at this point, the water has got slow velocity. And there's less power, it's less powerful. That is why there's deposition and why there's erosion. So basically, we're worried about this part. There's high velocity on the outer bend, and meaning to say, with the high velocity, the river has more erosive power, causing erosion at 11 and deposition at 10. Right, we are applying the concept of a meander here. We are focusing on the bend along a river channel. We are applying the basic concepts of the outer bend and the inner bend of a meander. Right, then we go to GIS, which is our last part. The vertical aerial photograph. Let's go to the question. The question is asking about the vertical aerial photograph used to make the orthophoto map. Yes. Is it a high or low resolution? That is a high resolution. Why are we saying it's high resolution? The features are clear. You can actually see the houses. You can see the river. You can see the roads. You can see everything there. It's almost clear. So it means it's a high resolution. There were many pixels, and pixels were smaller, used to make that image. The reference of the topographic map represents, is it spatial or attribute? Reference of a topographic map, we have coordinates in terms of latitude and longitude. So that is spatial. Spatial gives us the coordinates of the feature, and attribute gives us the characteristics or descriptive data of a feature. So the map coordinate, the map reference, it just gives us the coordinates of the feature. So it's spatial data in that effect. How does this data, to the question above, assist in identifying feature J on the topographic map? How do we use spatial data to identify feature J on the topographic map? Our feature J is here. How can we use spatial data to identify feature J? Right, for us to be able to identify feature J, one thing, we need the coordinates. With spatial data, we get the coordinates of the feature. Where is it located? On which line of latitude and which coordinates of longitude? Then we're able to identify this. And also it gives us information about the shape of the object. What kind of a feature is it? How does it look like? For us to be able to see what kind of a feature is this one, we can figure it by checking on the shape, how it is portrayed on the map. So it gives us the coordinates and also the shape of the feature, and we'll be able to identify that particular feature. Then define the term buffering. That's the next question. Buffering, that is a concept. And the question is asking about buffering. Basically, it's a concept where you need to apply the understanding of the basic concept. We cannot define a concept using the same words or using the same terminology, but terminology might differ. But as long as it is addressing the basic geographical effect to that particular concept, then it becomes a correct response. So if I am to give my own definition of buffering according to my own geographical definition, I would present buffering as demarcation around a geographical feature. Putting a demarcation around a geographical feature. That is how I can define it in simple understanding. Or putting a demarcation, or in simple terms, a boundary around a feature. That is buffering according to simple understanding. If you are buffering a river, we are having Clip River, then we don't want development to interfere with the river. We plant trees here to show that this is now the area of the river. There should be no human activities happening here, or there should be no development happening here. This is buffering. We've put a boundary. These trees are resembling that no human activity must interfere here. They are acting as a boundary. Or we put a fence along the river to protect people from accessing the river. That is also boundary. That is also an effect of buffering. We are trying to prevent human activities' influence on the river and ensure that they do not interfere with whatever is happening inside the river. So it's buffering in that dimension. Right. Move on to the next question, which is our last question for the paper. Right. How would buffering at 12 protect the quality of water in the Clip River? Buffering at 12, we are using the orthophoto map. There's evidence of buffering at point 12 on the orthophoto map. Let's check our 12 is there. There is some boundary along the Clip River as indicated by 12 there, definitely. How does it protect the quality of water into the river? Right. What you can say there, you can say that buffering there ensures that no development takes place too close to the river. If there is a buffer zone there, it means definitely there's no development that is going to take place too close to the river. And how does that help enhance reduced pollution of the river? is going to protect the quality of the water by limiting development too close to the river. If there's a buffer zone, it means human activities cannot happen too close to the river, and they cannot influence the quality of water into the river. And hence, we have safe water in the river because of limitation of human activities too close to the river. People are limited from influencing the quality of the water by the buffer zone. So basically, when I'm looking at buffering, its influence on the water quality, it helps to attain better quality of water and safer water because we limit the influence of human activities on the river. They are limited from directly accessing the water resource because of the buffer zone or the boundary which would be put in place. And at the same time, that will help sustain the water resource in the catchment area as part of water management, like the previous question in geomorphology. Right, basically that was the paper. From my own rating of the paper, I think the paper